Hi everyone. Today, now that we've learned about series circuits and parallel circuits, we're going to be looking at some more complicated circuits. Circuits that have resistors in parallel and in series. We can see from this example circuit that if we have two light bulbs that are in parallel with one another, like the pair of light bulbs on the right, then the current through each one will be less than a light bulb that's in series with the pair, which is why the two light bulbs on the right are so much dimmer than the light bulb on the left. Now, in real life, we don't really get extremely simple circuits. Circuits will often have resistors both in series and in parallel. So the current drawn from the power source can be found by finding the effective resistance of the entire circuit. You can't just pick one resistor and say, oh, that'll figure out the current drawn from the battery. You have to look at the entire circuit at once and calculate its total resistance. Luckily, we're now in a position where we can do that. We treat all of the resistors in the circuit as if they're one big resistor, and we do that by grouping the resistors together and treating them as just one resistor, and then grouping that pair with another set of resistors until all of the resistors are just one big group with one effective resistance. So let's take a look at an example. What would be the effective resistance of this set of resistors? We have two resistors in parallel, and the combination of resistors is in series with a third resistor. All of the resistors have a resistance of 1 ohm. In order to figure out the total resistance, we're first going to look at this pair of resistors as a group. We'll find the total resistance of A and B together, and then treat that whole thing as one resistor, RAB. This RAB is then in series with resistor C, right? And so then we can use our series equation to figure out the total resistance. To find the resistance of the parallel resistors A and B, we use this equation. Seem familiar? So 1 over the total resistance of the pair equals 1 over 1 ohm plus 1 over 1 ohm, which gives us, of course, 2 over 1, which is the same as 0.5 ohms as RAB. This makes sense, right? We've just spent some time looking at the resistance of parallel circuits. So RAB, this whole thing here, can be treated as just one single resistor with a resistance of 0.5 ohms. So if we have a resistor with resistance 0.5 ohms, and it's in series with resistor C, 1 ohm, what will the total resistance of the circuit be? Well, it'll just be 0.5 plus 1 amp, right? Because series circuits are easy. That gives us 1.5 ohms. So putting these three resistors together like this gives a resistance of 1.5 ohms. Let's take a look at what would happen if we put a power source of 6 volts here. The total resistance is going to be 1.5, right? 1.5 ohms. And the voltage is going to be the 6 volt that we supply it with. So the current through it will be 4 amps, right? And it will go, of course, from positive to negative. So the total current drawn from the battery is going to be 4 amps. Now, if we treat the pair of resistors on the left, A and B, as a single resistor, then there'll be 4 amps flowing through that resistor and 4 amps flowing through C. But let's look more closely at A and B. Because the current has to split up when it goes through A and B, it'll split up in equal parts, same resistances, and so 2 amps pass through A, 2 amps pass through B, and all 4 amps pass through C. Makes sense, right? Everything's all worked out. So let's look at a different example. Once again, we have 3 resistors in a circuit together. Some are in parallel and some are in series. So in order to figure this one out, we're going to take A and B as a single group again, because they're nice and close together. We can then treat AB as just one big resistor, and this one big resistor is then in parallel with C, right? So to find the resistor of series resistors, that is A and B, which are in series with one another, it's just 1 ohm plus 1 ohm, which gives us 2 ohms. So the total resistance of this branch of the circuit is 2 ohms, and we can treat A and B as just one big 2 ohm resistor, right? So we have a 2 ohm resistor in parallel with a 1 ohm resistor. The total resistance of these will be 1 over 2 ohms plus 1 over 1 ohm. So our total is going to be 2/3 of an ohm. That is 0.666666 and so on ohms, right? Now what happens when we connect this to a 6-volt power supply, like we did to the last one? I equals V on R, and substituting in 2/3 and 6, we get 9 amps being drawn, which, as you'll notice, is more than twice as large as when we had the 3 resistors set up the different way, right? So of the 9 amps drawn from the battery, 3 amps will flow through resistors A and B, because their total resistance is 2 amps, and 6 amps will flow through resistor C. So we have the 2 ohms times 3 amps gets us 6 volts, and 6 amps times 1 ohm gets us 6 volts. So the voltage drop across this resistor and this giant resistor is the same. Of course, if we were going to look at A and B, then there would be a voltage drop of 3 volts across A and then 3 volts across B. Now, the current through a resistor is what's important, because the current is what determines how much heat is radiated or how much power is radiated from the resistor, whether it's a light bulb or a heating element or whatever. The brightness of a light bulb is a direct reflection of the amount of current passing through it. The higher the current, the brighter the light bulb. If multiple light bulbs are in the same circuit, how exactly will the brightness change? And does it matter if we put them in series or in parallel? Well, let's look at what happens when we connect light bulbs in series, which might look something like this. You can see in this photograph the light bulbs are sort of joined together with the power source as though they're links in a chain. So they're in series with the battery. So the combined resistance of the light bulb is larger than the resistance of any one light bulb, which decreases the current through them, right? The effective resistance of the circuit is quite large. And the more light bulbs we add to the circuit, the less current we'll get flowing through it because we'll have a higher resistance. So the more light bulbs we add, the dimmer the light bulbs get. All right, what happens if we connect them in parallel instead? If we connect light bulbs in parallel, like in this photograph, the total resistance of the circuit will get lower. The voltage drop across each light bulb will of course be the same for every light bulb, which means that the current will be the same in every light bulb as well. The more light bulbs we add, the more current we draw from the battery. No matter how many light bulbs we connect, we're always going to get each one glowing just as brightly as the last one, at least until the wires get hot enough to cause a malfunction in the power supply itself. So that's the end of the theory. We've learned a bit about more complex circuits and how we can calculate the total resistance of resistors that are in series and resistors that are in parallel in diagrams that have more than 2 resistors. Let's go on to some questions.